We are Team 23 from the Department of Biomedical Engineering, and we created a novel smart shunt sensor for hydrocephalus.
Hydrocephalus is a chronic medical condition caused by an excessive buildup of cerebrospinal fluid in the ventricles of the brain. Like the video shows, as fluid accumulates in the head, it starts to put pressure on the brain. This can be extremely painful for patients and can lead to death if left untreated. Over 1 million Americans live with hydrocephalus, and this condition certainly does not discriminate when it comes to age. 1 in 1,000 babies are born with hydrocephalus, and 1 in 100 senior citizens develop normal pressure hydrocephalus.
The current standard of treatment for hydrocephalus involves using a shunt to drain excess fluid surrounding the brain to somewhere else in the body where it can be safely absorbed. A shunt is made up of three parts: a ventricular catheter, a valve, and distal tubing. As fluid starts to build up in the ventricles, the shunt enables it to flow to an absorption site usually located in the abdomen of the body. Although shunts are life-saving devices, they are notorious for having high failure rates, difficulty diagnosing failure, and limited control options. This project will enable a major improvement in hydrocephalus care since the introduction of shunts in the 1950s. A major reason why shunt technology has not advanced in many decades is that there are no sensors that can determine when and why shunts fail. We came up with a sensor device that can be added on to commercially available shunts to monitor the treatment of hydrocephalus. The primary purpose of this device is to provide data on patient condition and shunt function. One way our device is able to do this is by measuring flow rate. Our team created a flow sensor that can be used with existing shunts. The flow sensor has a built-in optical system, which is complemented with an integrated circuit and Bluetooth module. These internal components of our device are powered by a receiver inductive coil that is able to receive 5 volts across the scalp, where an external inductive coil is connected using a magnet. This external coil is powered using a 9-volt battery, which we envision would sit behind the ear for purposes of our demo. Our team was able to create a low-cost, integrated circuit by milling a customized circuit board and combining it with a small microprocessor. The trinket shown below is approximately the size of a quarter. The following video shows how all of these components are put together in one package. At the very bottom is the Bluetooth module. This is responsible for transmitting data to an external computer. Behind the Bluetooth is the microcontroller, which collects data from the sensor. And finally, at the very top is the circuit board with operational amplifiers and resistors attached.
The outer transmitter powering coil would ideally be worn behind the ear on the head. A compartment for the magnet on the external coil is shown here. There is an identical powering coil on the inside of the head that has a magnet as well. The two magnets are attracted to each other through the skin, and the outer powering coil will begin to power the device implanted inside.
Here you can see all of the parts aligned as they would be in the body. On the outside of the body is the outer coil, and inside of the body is the internal coil, the internal electronics, and the sensor compartment. This is the sensor compartment which holds the optical system, flow sensor, and photodiode. It consists of 3 parts: the optics base, optics cover, and sensor holder. The optical system shown here focuses a light spot onto the sensor, which reflects that light at varying angles. This light deflection is measured by a photodiode embedded in a PDMS cover above the sensor tip. Here you can see how light enters the ball lens from the LED and is focused onto the fiber. It then deflects off of the sensor tip. As flow increases, the sensor deflection increases and the light is deflected at a larger angle, and vice versa.
The flow sensor will provide different light intensity measures depending on the flow speed of cerebrospinal fluid. The collected data will be transferred through Bluetooth into an external computer. Transmitted signals can be analyzed by measuring the intensity of flow. Using a computer will enable it to analyze the pattern of overflows and differentiate it from regular flow rate fluctuations.
We must verify that the new integrated device is capable of measuring the necessary flow rates. This photo shows the experimental setup that we used to collect preliminary results before the updated sensor compartment arrived. During testing, liquid was pumped through the sensor compartment with the pump pictured here. This video shows preliminary results that were collected as liquid was pumped through the flow sensor. This graph shows results from a previous experiment. Ideally, the results from the integrated device would be similar to these. Although our testing was cut short, we were able to show that the LED effectively illuminated the flow sensor tip, the photodiode was able to detect a change in flow rates, and the device was able to successfully send information from the photodiode to a computer via Bluetooth.
For the future work, testing and fine-tuning the sensitivity of the flow sensor and the complete setup will be the primary objective. Then, as previously mentioned, analyzing and differentiating critical overflow from a regular flow rate fluctuation will be the next task.
Thank you for watching our presentation. We really hope you enjoyed it.